On the 23rd of June 2025, the Vera Rubin Observatory published the first observations done with the camera which will perform the largest survey of space and time. Let's look at those images through the eyes of an astronomer. Welcome back to Boring Astronomy. I'm Alessandro, your astronomer next door.
Boring astronomy.
In case you're wondering, I'm Alessandro. I have been in astronomy for the past 20 years, and I'm here to share with you some of the things that I've learned along the way. I first heard about the LSST project, which back then had a completely different name, in 2005, so literally 20 years ago. It was a brand new project, was building on the experience of the Sloan Digital Sky Survey, and I got very excited. The idea back then was to cover the whole sky every week for 10 years. Since I was at the end of my PhD and I was working on variable stars, and I still am working on variable stars, for me LSST has been the project I've been waiting for. The best way to access information about LSST is through their website, and they just made a new one, so make sure you get to the right one. So rubinobservatory.org. And because I'm an astronomer, I normally go to for scientists. Let's use this visualization to show that this telescope has a very interesting optical design. The light bounces 3 times before reaching the camera. This is needed because one of the goals that they wanted to achieve is to have good image quality over a wide field of view. To have a wide field of view, you need to have a compact telescope. As a rule of thumb, if you have a telescope which is very slim and long, that will have a very narrow field of view. If you have a telescope which is compact and fat, that telescope is going to have a very wide field of view. And this telescope is quite broad and strong. So this telescope achieves what it was designed to do. What really makes it special is this combination of wide field of view and a primary mirror, which is 8 meters across. This product, field of view and the size of the primary mirror, has a name. It's called etendue. And the larger the etendue, the more powerful the telescope is for surveys. And for the past 20 years, LSST has been the gold reference for all survey telescopes. The big problem of having such a large field of view is that most famous astronomical objects are smaller than it, but much smaller than it. So it is difficult to find an object which you can take a pretty picture of. Let me give you an example. This galaxy is M87. We featured it as one of the astronomical objects of the month. This is a relatively large object. So in this case, you're looking at it on ESA sky, and the field of view here is 13 arc minutes times almost 7 arc minutes. For normal telescope, even an 8 meter class telescope, but with a normal optics, this is a relatively generous field of view. What happened to me is when I was commissioning a telescope with an instrument of half a degree times half a degree, I said, well, let's point at M87. It's big, it's bright, it's famous. It's going to be easy to find. Let's see what happens if I have half a degree times half a degree. Alright, I'm almost cheating. Now I have 1 degree in the x-axis and I have half a degree in the y-axis. So you have to imagine just cropping from here to here. All of a sudden, what was obviously a galaxy, all of a sudden now it almost looks like a very bright star. If you don't expose long enough, these objects, they can all look very much the same. And you can imagine if you have a field of view like the telescope of LSST, which has 3.5 degrees on a side, all of a sudden the galaxies, they sort of look very, very small. So it's difficult to emphasize their beauty. So a few months ago, when I saw the picture of all the astronomers and technicians in the control room of the Vera Rubin Observatory taking the first image of what will be LSST, I was very, very curious. I wanted to know what was the first field that they observed. Alright, so this is one of the three. And this is, again, the Virgo cluster. So this is one part of the Virgo cluster, and the images are displayed with a software made in France, in Strasbourg, called Aladdin Light. Of course, you can see there's a lot of pretty galaxies. Honestly, I didn't even look at the galaxies. When I first saw this, the first thing I noticed was there is a lot of orange and red points there. Most of the faint targets are red, so it probably means that they had to expose a lot in the red. And the other thing that caught my eye was the bright stars. You may or may not remember, when the first light images of the JWST became public, there were these 6 spikes. We only have 4 spikes here. The spikes depend on the optical design. The actual shape of the PSF is actually a cross. I'm ready to bet money on this. And so the fact that you have this red cross, but you also see this red cross, and it tells me that to do this image, they had to some images taken over more time. And it also tells me that they had to do something similar with the blue and with whatever they used as a green filter. If I move a little bit further, I actually see a lot of points. The important thing to my eye is the blue points and the red points. They don't seem particularly different. They do seem all very, very round, and as I move across the image, I don't see them changing the shape. And this is crucial for this kind of project. I heard some months ago, even some professional astronomers saying that since this telescope has a primary mirror of 8 meters, that it would have a resolution of 1 arcsecond. 0.1 arcsecond or less, and would be comparable with telescopes in space. And obviously this is nonsense. The telescope is on the ground, so for the way that this telescope works, the telescope is limited by the quality of the sky of Chile, which is possibly the best sky in the world, but still is limited by the atmosphere. The images will normally be between 1 arcsecond to 0.5 seconds, exceptionally less than 0.5 arcseconds. No way is going to be less than 0.2 arcseconds. This image puts together the Lagoon Nebula and the Trifid Nebula in Sagittarius. This is going to be very, very interesting to see once the actual feeds files are going to be published, because performing photometry in this complicated environment is going to be a challenge. Now, why is this telescope so interesting? Well, this telescope is going to observe the sky in 6 filters. Every 3 days is going to observe all the observable sky in one filter, then it's going to change another 3 days in another filter, then another 3 days in another filter, and so on. And it's going to do it for 10 years. Eventually it's going to build a fantastic set of light curves. Everything that moves or changes in brightness is going to be discovered by this telescope. They have already unveiled a few thousand new asteroids just because they have a big telescope and they observe faint. To the risk of sounding boring, but then again, this is boring astronomy. Whenever you have a wide field of view, you are bound to be swamped with asteroids. One thing which is extraordinary is this telescope is going to produce terabytes of data per night. And these data are going to be sent in real time to SLAC in California, United States, for data processing. And within 1 minute from closing the shutter, we already are going to receive alerts and notifications for any variable object which is in the dataset just observed. This telescope and this project are going to change the way we deal with astronomical transients forever. Coming soon, a video about the preliminary data from LSST, which was done with a smaller camera, but very much in a similar fashion to how LSST is supposed to work. If you like this video, click like, and if you would like to hear more about boring news in the world of astronomy, click and subscribe, and don't forget to subscribe to my newsletter. I'll talk to you soon. Ciao.